Welcome back. Now we are going to finish off section 4.2. So we are picking up with the oxidation states of elements in compounds. So this is building on redox reaction. So there are some redox processes where there is no transfer of electrons. Okay, for instance, hydrogen gas and chlorine gas react to form hydrogen chloride. This forms a covalent compound, so you don't really see explicit electron transfer. But what is happening is that the oxidation state or the oxidation numbers of the elements can change. Okay, and what an oxidation number is it's the honorary charge, if you will, of the atoms in a compound if this compound was ionic. I know that sounds really weird, but if HCl, for instance, was ionic, each of the atoms in that compound would have their own charges or oxidation states. So we have some rules. It's not just two rules split up on different slides. If you have an atom in its elemental form, its oxidation number is 0. This includes our diatomics. Okay, so remember the diatomics: H2, O2, N2, F2, Cl2, I2. What am I forgetting? Br2. Haha, there's the stuff. Okay, so these guys have an oxidation state of 0. Okay, their elemental form is as a diatomic molecule. Everything else, though, if you see, solid sodium, that's its elemental state, 0. If you have a monatomic ion, okay, so you have sodium ion, its oxidation number is the same as its charge. For instance, Na plus, okay, has +1 charge and +1 oxidation number. Now, there are some common oxidation numbers that you need to be wary of. For instance, hydrogen is either +1 oxidation number when combined with a nonmetal, but when it's combined with a metal, it is -1. Okay, so in that example of HCl, okay, it's combined with a nonmetal, so that means it's +1. Oxygen, most of the time, is -2. Okay, so oxygen generally has an oxidation state of -2. If it's in a peroxide compound, if it's O2, 2-, then each oxygen has an oxidation state of -1. If you have a superoxide, super rare, it's going to be -1/2. If it is combined with fluorine, it can have different oxidation states, and it's going to have a positive oxidation state. But the most important one to know is that it is -2 in most compounds, 99% of the time. For halogens, fluorine is always oxidation state of -1. Always -1. The other halogens in general are -1 unless they're combined with oxygen or another halogen. Okay, then they're going to have a positive oxidation number. That will vary, and you have to solve for it. Okay, so going on that, we figured out that in HCl, hydrogen would be +1 since it's with a nonmetal, and chlorine here would be a -1 oxidation state. And the sum of the oxidation numbers for all the atoms in a molecule, or if it's a polyatomic ion, it has to equal the charge on the molecule or the ion. So going back to HCl, okay, this overall charge is 0. So +1 -1 gives us an overall charge of 0. Don't worry, we're going to look at some examples you better understand. So let's figure out some oxidation numbers of some elements in some species. So this first one is H2S. So looking at this, we have hydrogen bonded to a nonmetal. So that means hydrogen has an oxidation state of +1. And I have 2 of them. So that's a total of +2 from the hydrogens. So since this overall needs to equal 0, so this +2 plus x, if you will, needs to equal 0. Solve for x, subtract 2 from both sides. X equals -2. So that means that sulfur has to have an oxidation state of -2. I know I just did all the work right there, and it's lower also, but so there you go. Using those rules, we can figure out the oxidation number for sulfur. Now here's another one, SO3 2-. The first thing we need to see here is that our overall charge is -2. Okay. Now oxygen, 99% of the time, has an oxidation state of -2. Okay, so I have 3 of them. Okay, and so I need to figure out what my sulfur is, plus x. So I have -6 plus x equals -2. Add 6 to both sides to solve for x. And that gives us +4. So the sulfur has an oxidation state of +4. So oxygen has an oxidation state of -2, sulfur +4. All right, Na2SO4. So let's do this kind of separately. Let's separate this into the cation and anion. So sodium is a group 1 metal, therefore its oxidation number is the same as its charge. So sodium ion is +1. There we go. And SO4 has an overall charge of -2. Okay, so we know for SO4, I need -2. Oxygen has an oxidation state of -2, and I have 4 of them. So plus some x for sulfur. So I have -8 plus x equals -2. 8 to both sides. So x equals +6. So the oxidation state of sulfur is +6. The oxidation state of oxygen is -2. And the oxidation state of sodium is +1. Now, remember how we first defined what is oxidized and reduced? We used oil rig. Oxidation is loss of electrons, reduction is gain of electrons. So that still holds true, but we have another definition we can use. Oxidation is the increase in oxidation number, and reduction is the decrease or reduction in oxidation number. So this is all inclusive. This holds true for every kind of redox reaction. Here's an example of a combustion reaction. So a combustion reaction is when you have a reductant or a fuel reacting with an oxidant. Usually it's O2, molecular oxygen, not always, for instance, the example here, react to produce heat, sometimes light, in the form of a flame. So for example, you react solid aluminum metal with ammonium perchlorate solid, and you make aluminum oxide, aluminum chloride, water, and nitrogen gas, and this gives lots of heat, light, and it's a nice propellant. So here's another example. We have single displacement or single replacement reactions. And these are redox reactions where an ion is in solution is displaced or replaced by the oxidation of a metallic element. For example, solid copper reacting with aqueous silver nitrate make aqueous copper nitrate and silver metal. So copper here goes from an oxidation state of 0 to an oxidation state of +2. On the product side, as you see it with that, now it's an ionic compound, and there's 2 negative ones of the nitrates, now it's +2. Whereas the silver went from an oxidation state of +1 to now an oxidation state of 0. Okay, so copper here had an increase in its oxidation state, so it was oxidized. Whereas silver had a decrease in its oxidation state, a reduction in its oxidation state, so it was reduced. This is what this reaction actually looks like. You literally, the copper nitrate. Yeah, copper nitrate. Copper generally has a blue tint to it, fun fact. So you end up forming this really pretty blue liquid, as well as then a silver metal that comes out of solution. Now this next part is the entire reason I have this half of 4.2 in a separate video. Balancing redox reactions via the half reaction method. This is I don't want to say it's hard, it's super complicated. It just takes practice, and it's not something you want to rush through. A lot of times students just try to balance it really quick and get on with their lives. Sorry, you can't really do that here. You've got to take your time. You can't really balance these just by looking at them. So we have to use the half reaction method and go from there. So there are some steps. I'm going to talk about the steps, and then we're going to go through some examples so it's a lot easier to understand it through it. So the first thing you want to do is break up your reaction into half reactions, the oxidation one and the reduction one. Then you're going to balance everything in the reaction, in each half reaction, except for oxygen and hydrogen. The next step is to balance the oxygen atoms by adding water molecules. So as many oxygen as you need to balance, you add that many waters. Then you balance hydrogen by adding H+ ions. Then you need to charge balance. Make sure you have the same overall charge on both sides of the reaction by adding electrons. Now, if you need to multiply each half reaction by their coefficients by the smallest number of integers to make sure that each half reaction has the same number of electrons. Then you're going to add your half reactions together, remove species that appear on both sides of the equation. And what I want to add here is to make sure your electrons cancel. Okay? They'll be on the left side of one half reaction and the right side of the other. You need to make sure you have equal numbers of electrons. Okay, so now this is step 7 is the end for acidic conditions. So if you're told to balance in acidic conditions, you go through step 7. Now, if you are told, though, to balance in basic media or the basic solution, basic conditions, then there's some extra steps. Before I get to that, one thing I want to touch on is in an acidic conditions, you can have H plus in acid. OH minus, though, is not okay in acid. But if we're in a basic media, H plus is not okay to have. OH minus is okay, though. So, if you're told to balance in a basic solution, you're going to start by adding OH minus to both sides of the equation, okay, equal to the number of H plus ions. So if you needed to add, you have, let's say, 5 H plus ions on the product side. Then you would add 5 OH minuses to the product side, and then you would also do 5 OH minuses to the reactant side. It's just like in an algebraic equation where you, if you were to add something to both sides, you're adding 0. They would cancel each other out, right? Same type of mindset. So then what you're going to do is you're going to look on each side of the equation and see where you have H plus and OH, combine them to make water. And then you look on each side of the arrow, look for water on both sides, cancel them out. Then make sure that your number of atoms and your charge are balanced. And I know I just threw a lot of information at you. And like I said, we're going to go through an example. 2 examples, one for acid, one for base, and I really hope that'll help it make more sense. So here's our example. We're told dichromate ion and iron 2 ion are reacting to make iron 3 and chromium 3 in acidic solution. Notice also we weren't really given full ionic compounds. They've already kind of gotten rid of the spectator ions, makes our lives easier, right? So what we're going to start by doing is breaking this up into half reactions. So I'm going to go, okay, this has chromium and chromium. This has iron and iron. So now I've identified my 2 half reactions. Okay, each one has a reactant and a product that have an element in common. So I have an Fe2 plus becomes Fa3 plus, and Cr2O7 minus becomes Cr3 plus. So these are my half reactions. My next step is to balance all elements except oxygen and hydrogen. So if we look at this, the iron, the atom numbers are already balanced. I already have 1 iron on each side. But for the chromium, notice I have 2 chromium on my reactant side and only 1 on the product. So I need to add a 2 in front of Cr3 plus. So that's step 2. Step 3, you're going to balance your oxygens by adding water molecules. Sometimes you have to do this to both half reactions, sometimes neither, sometimes only 1. In this case, we don't have any oxygens in the iron equation, so that's fine. But in the chromium, I have 7 oxygens on the reactant side. So I need to add 7 waters to the product side. So now I have 7 oxygens on either side. Step 4, balance hydrogen by adding H+. So when I added those 7 waters, that gave me 14 hydrogen in the process of adding 7 oxygen. So now I had 14 hydrogen on the products, so I need to put 14 hydrogen on the reactant side. So now my hydrogens are balanced, my oxygens are balanced, and my chromiums are balanced. Nothing to do for the iron. But we're not overall balanced yet. Actually, before I go there, we need to balance the charges. Okay, so we need to make sure that, look at the total charge on each side of the equation. So I have Cr2O7, 2 minus, so that's a charge of -2. Plus, I have 14 plus 1s here. So that's plus positive 14. This equals a charge of positive 12 for the chromium on the left. The product side of chromium, I have 2 3 pluses, so that's plus 6. There's 0 charge on the water, so this is a total of positive 6. Okay? For the iron, on the reactant side, I have a total charge of positive 2. On the product side, positive 3. Okay, so we can see neither of these half reactions are balanced as far as charge goes. Keep that in the back of your head. So step 5 is to balance charge by adding electrons. So remember, electrons are negative charges. They have a charge of -1. You add as many electrons as you need to one side of each half reaction to make sure that you have the same charge on each side. No, you don't need to have a charge of 0 on each side. Just make it the same. So, like we said, with the iron, I had +2 on the left and +3 on the right. So if I add 1 electron to the right side, so now I have +3 plus a -1, that gives me +2. So my charges are equal now on the reactant and the product side. For the chromium reaction, I had a total of -2 plus +14. I had +12 and +6 on the right. So to make it's easy, you can bring the charge down. You can't increase charge. So to do that, I add 6 electrons to my reactant side. So that's plus -6. That gives me a total charge of +6 on the left. Okay, so now we have +6 on both sides. Check. +6 on the left, +6 on the right. Now, the next thing in step 6 is you look at your half reactions and you need to have the same number of electrons in each half reaction. So from the chromium half reaction, we had 6 electrons. But from the iron one, at first, I'll erase these in a second, we only had 1 electron. So I need it to be the same. So to do that, I'm going to multiply every coefficient by 6. 1 times 6 is 6. Okay. And boom. Now, one thing I recommend that your book doesn't do, but has always helped me, is kind of like in algebra. I like to rewrite, when I start kind of stacking my half reactions, I like to stack them so that the arrows are on top of each other so I don't get the sides mixed up. So then I have 6Fe3 plus 6E minus, 6Fe2 plus, and then here I have Cr2O7 2 minus, plus 14H plus. Oops, I can put it here. 6E minus. Doesn't matter where you put it. 2Cr3 plus 7H2O. So for me, I'm a very visual person. This just always helped me know, okay, this is where my arrow is. Think of those arrows as an equal sign. And think of this as a system of equations. You're adding them up. So step 7 is to add your half reactions. I'm going to go back to the way I wrote it. They like to just put everything in one line. I do it this way and go, okay, this is the same on both sides. You can always just do like they do it. They write everything and then go through and cancel. They go, there's 6 electrons, there's 6 electrons. There you go. If you have any other redundant species, cancel them out. But your electrons always cancel. You never have electrons left over. If you do, you need to go back and fix things. Oops, cancel. All right, so once we get rid of the electrons and anything else that might be the same on both sides, then you get your simplified balanced equation. And if you were to go through this, you see that everything, as far as our numbers are balanced and our charge. So I have 6 2 plus, that's +12, plus -2, plus +14. So that's 6, 25, 24 plus 24. And on my product side, I have +18 plus +6 equals +24. Charge is balanced on both sides. Doesn't have to be 0 on both sides, it just has to be the same. And there's a final, they also are showing you a final check. Atoms, you have the same atoms on both sides, same charge on both sides. So it's a great way to check your work and make sure everything checks out. All right. So this is a reaction. This one's not in your book as an example, but I actually do not like the example that your book gives in the Check Your Learning. I wouldn't give you one like that. That one's honestly... So this is a nicer, easier to understand redox reaction in basic conditions. Okay, so our first step, we got to figure out our half reactions. So I see silver, silver, zinc, zinc. And sometimes what I do is I try to do, like, kind of divide my paper in half, and I do each half on each side. So I have silver going to H2O and zinc 2 plus. Going to zinc solid. Okay, so our first step, balance everything that is not hydrogen or oxygen. So my zinc is balanced, 1 zinc on each side, but my silvers are not. I need to put a 2 in front of this reactant side. The next step is to balance oxygen by adding water. I'm going to use a different pink ink color here. So nothing on the zinc, but I do need to add water for silver. I'm going to add it only to the left because I need only 1 oxygen on the left-hand side. And then we need to add hydrogen to balance, or H plus, to balance out oxygen. Let's see, I'll move that over later. So this is going to need 2 H plus. All right, we are cooking now. Now, our next step is to add electrons to balance our charges. Get another pen color here. Let's do green for electrons. Why not? So what we first need to do is look at our charges on each side for each half reaction. So what we should notice here is on the left side for silver, water is an overall charge of 0. The silver here is solid silver. It's a charge of 0. This is overall 0. But on the right side, I have 2H plus. So to get this to be 0 charge, I need to add 2 electrons. So now that's plus 2 plus negative 2, overall 0. On my zinc side, I have a positive 2 on the left and 0 on the right. So then to the left-hand side, I want to go ahead and add 2 electrons. So then I have positive 2 plus negative 2, 0. All right. So now we have our general balanced half reactions. Let's go to another pen color. I'm going to go to dark red. So now let's go ahead and stack these guys up and make sure everything is matching properly. H2O plus silver. I'm going to just not worry about the states that matter right now. They don't matter. That's right, I said it. Okay, and then our other reaction is zinc 2 plus 2 electrons. Here comes zinc. And look at that. We have the same number of electrons on both sides, so we don't need to worry about multiplying by a coefficient. They already cancel as they're supposed to. So then we can write our resulting reaction, plus 2Ag, plus zinc 2 plus, G2O, plus 2H plus zinc. And we're done, right? Nope. Nope, we're not. Basic conditions. That means no H plus. So, to get rid of H plus, our next step is to add OH minus to both sides of the reaction. So I have 2H plus on the right, so I need to add 2 OH minus And then I need to do that on the other side as well, on my reactant side. So 2OH minus gets added. Okay? And then we go, okay, I've got 2 H pluses and 2 OH minuses. Those are going to combine to make 2 waters. So now what you should hopefully see is I have 2 waters on the right and I have 1 water on the left. If this were an algebraic equation, we could say this is x on the left and 2x on the right. If I were to subtract x from both sides, it would be gone from the left, and I would be left with just 1x on the right. So that's what's happening here with the waters. Okay, so I have 1 water on the left, 2 waters on the right. So this water goes away, one of these waters goes away, and now we can write our resulting equation. 2OH minus aqueous plus 2Ag solid plus zinc 2 plus aqueous times Ag2O aqueous plus solid zinc plus water liquid. And that is our balanced equation in basic conditions. We did it. So I have a feeling I'm going to have lots of questions. It's perfectly fine. For the homework video this week, I will have I'm going to try to get the homework posted this week for you guys, but the one thing I want to say is you might not be able to do much of it until we've gone through everything next week as well. But if you want me to go over more examples of this, please email me, let me know. I'd be happy to do that for a video this week if you guys would like. The other thing we can do is I can just do a bigger video next week on homework and any other questions you may have. Doesn't matter to me. It's whatever is easiest for you guys. That is what I'm here for. I am here for you. With that, stay safe. Don't work too hard, and I will see you guys soon.